Yes, good morning, Bhavna. Can you confirm that I am audible and screen is visible?
Yes.
Okay. So we'll start. Today will be the last lecture. Anyways, we won't be able to finish what is required out of the course. So you will get maybe 2 or 3 lectures in the recorded sense. In the coming week, I will basically upload them. But today we would be finishing up with most of the part of QPSK. We'll start QPSK and finish up with it. So last time we were discussing BPSK, and there were, I think, 2 to 3 important details which were mentioned in the textbook, but they didn't have that much discussion on them. So I elaborated on each of those, and I would say that you should go through the notes, go through the textbook, and solve some problems. You will understand BPSK quite well. But one important thing to say is that this BPSK as a standalone, uh, if you try to study, then a lot of questions will arise. Okay, and so in order to address those questions, you must have sound base of whatever we have done up to now. Okay, before BPSK. So the studying BPSK standalone, you will say that what was required to study all the things which we have done earlier. But if you try to question yourself on BPSK, then you will feel the need of what we have done before. Okay. So BPSK, you have two possible. You were saying that in BPSK, 2 possible phase values you took, 2 possible phase values were chosen. Phase values were chosen of the carrier, chosen of the carrier wave. One was 0 and other was, I think, pi. Okay. So 2 bits of information were encoded. So it was possible to encode 2 bits of information. But what about we take 4 possibilities? What about we take 4 possible phase values? Let me write equispaced. Important to write that. It means they have to have some uniform structure or some symmetry so that transmission and reception is an easy phenomenon. Okay. 4 possible phase values of the carrier. So right now I am not elaborating on the term QPSK or on the name QPSK. Once you will build all of this, we will get to know. Okay. So for example, those values be, for example, let's take pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. Okay, that is, let us say, on a circle, if this is theta, if this axis is, suppose you can say I am just drawing theta, is a 2-dimensional axis, this is pi by 4, and this is 3 pi by 4, this is 5 pi by 4, and this is 7 pi by 4. This is nothing but this theta. Okay, because this is pi by 2 as well. One possibility is this. You can ask me that there is another possibility. Why not take like this? One is this, one is this, one is this, and one is this. As per the definition, this is done, but I think, let me try. In the recorded lectures, I will try basically answering that which of the constellation would be preferred. Okay, but right now we will be studying this. Okay, which has now the problem is, the issue is that if you take this as a design, if this is my one of the phi axis, this is my phi 2 axis, suppose you can say. Okay, then if I take these constellation points, I will have components along both the basis functions. But if I take this as the constellation design, then I will have components only along one of the basis function. It means if I take this and this, so it will have components along only phi 1. If I take this and this, then it will have components only along phi 2. Okay, so one issue which you can see from this. With this as the case, the transmitted waveform SIT, how can you write it? So, SIT can be written as twice of E upon T. Now T is the symbol time. Note that this is not the bit time now, because in BPSK it was bit time, because it can encode only bits of information, it can only encode two values. Right now we will be encoding four possible. Let us see that. Cos of 2 pi f ct. So we said that we would be taking four possible values of the carrier wave, and those four possible values can be written like this. If I take this as the example, okay, pi by 4, where I will belong to 1, 2, 3 and 4. Now you can check. If I is 1, it is pi by 4. If I is 2, then it is 3 pi by 4. If I is 3, then 5 pi by 4. And if I is 4, then it is 7 pi by 4. Okay, and t will lie between 0 to t. You obviously know that we are considering waveforms which lie only from, or which are defined only from 0 to capital T. Okay, and I is like this. Let us define. So E, I have told that T is a symbol time. What is E? E is the transmitted signal energy. Energy per symbol. This is important because anyways this SIT encodes one symbol. So if I say that the energy of SIT over this time 0 to T is E, then it's obviously transmitted signal energy per symbol. Okay. T is a symbol time / duration, you can call. For T times a symbol will last. And what is F of C? F of C is some NC by T for some fixed integer, or some fixed integer NC. Okay, I think this I explained in the last lecture, that why do we do that? We do that so that in this time interval from 0 to T, or any time interval of capital T, we get integer number of cycles of the carrier. This basically leads to a well-defined waveform which is transmitted, as well as its detection. It will help in synchronization and several other things. We didn't go into that because our course anyways doesn't require us to think that much deep. It simply says that you first understand what these waveforms are, and all those associated issues can be done in another course, which generally is not offered at the BTech level. Okay, that would be given in the MTech level because it is more focused on communication engineering. Okay. Now what we can say is, once we have taken that there are four possible values, so obviously you can say that how many will be associated, how many bits you can encode, because there are four possible, 2 bits you can encode. Okay. Let me write it. So we can associate 2 bits with, 2 bits with one of the SIT. Of the SITs. Okay, obviously because we have four possible waveforms, S1, S2, S3, S4, so obviously you can encode 2 bits. Now the assignment. Can be gray encode, Now what is this? See, for example, if you have taken this as the constellation diagram, and this is the first bit with, I have not yet defined what constellation is. Now I will first define it and then we will study it. So gray encoding simply means that if I assign 0, 0 to it, so the two nearby symbols should differ with me in only one bit. So one possibility is 0, 1, another possibility is 1, 0. Okay, so from 0, 0 this differs only in one bit. From this 0, 0 this differs only in one bit. And if I choose, and now I have to do the same for this, so this should differ from this and this in one bit. So I'm lucky I have 1 and 1. Okay, so you can check that this 1 and 1 now. So one important thing is that the symbols which are exactly opposite to each other, they now differ in 2 bits, but the nearby ones, they basically differ only in one bit. Now what is the benefit of it? The benefit of it is, suppose you transmit this. Okay, you are transmitting this. I think this you must have done in Introduction to Communication Systems as well, but let me repeat it. Suppose you transmit this, and let me write and. In most of the cases, an error is made when let me write it in a more well manner, because this is not the way to do that. So what do you want to say is, you want to say simply that the cases received symbol belongs to either of the nearby decision regions. Now what is the meaning of it is, now you can see अभी आपने decision region discuss नहीं किया, but suppose you assume this is the lines, these lines represent the decision regions. It means if at all my received symbol falls anywhere here or anywhere, I will decide in favor of 0, 0. But mostly you will find out that whenever error happens, this dot, this received symbol shifts either to this place or to this place. It means ऐसा नहीं होगा, rarely it will go to this place. So this is a phenomena which is generally rare, or it will not happen in most of the cases. This will happen. So if at all this happens, so you will take a decision in favor of either 1, 0 if it lies here, or 0, 1 if it lies there. Okay. So in those scenarios, what is the bit error? Bit error get reduced by half. It means अगर आपने यहाँ 1, 1 डाला होता तो आपके bit error कितने होते? 2 bits में error होता. क्यों? क्योंकि if you decode it, you transmit it 0, 0 and you are decoding 1, 1. So 2 bits are in. But now, because of the gray encoding scheme, if you transmit 0, 0 and if the error happens in 1, 0 or 0, 1 is the decoded symbol, only 1 bit is in error. So this way you reduce your errors in the number of bits. Okay. So I will say, let me write it down, either of the decision regions. This leads to either 0, 1 or 1, 0 getting decoded, and it leads to only a single bit in error. I think this should be clear, because if you transmit 0, 0, suppose आपने 0, 0 transmit किया and you decode as 0, 1, so this is the correct bit and this is in error. Similarly, if you transmit 0, 0 and you decode, I think this, I'm just being very specific, 1, 0, but this is correct and this is in error. So by 1 bit only you are in error. So this is the benefit of gray encoding. Okay. Now, first of all, define what really is a signal constellation or constellation is. So what is signal constellation or constellation diagram? Okay, let me just write it. The set of message points slash the set of signal points slash message points. Now, what is it? First of all, what is it? Corresponding to the set of transmitted signals SIT is called a Now, once you represent this signal constellation on a graph like this or on a figure like this, then it is called as a constellation diagram. Okay. Once you represent it on axis is called constellation diagram. Okay, so let me explain it. So we had said that xit, let us say s1t, s2t, and suppose s1t. Now over the basis set, that is phi 1t, phi 2t, and this is phi nt, where we know that n is less than equal to m. Okay, we said that s1t will have some component along here, and this goes s1n. Okay, this has s21, this has s22, and this has s2n, because we knew that the subspace generated, or the subspace to which s1t to smt belong, let us say their basis function is, the basis set is phi 1 to phi nt. So if I try, I can write s1t as linear combination of these basis functions with components s11, s12, s1n. The way to obtain these components was just do the projection s1t over phi 1t dt and integrate it from 0 to t, because this is what we are considering as our domain of interest. Okay, so this will give you s11. Okay, so if I do the same, so we have this for all. I think we have done it before, but I didn't give you this tabular form. This I have just drawn right now itself. So this I can say is denoted by some vector, that is s1. Okay, this is a vector, and this is denoted by some vector s2. Okay, and this is denoted by some vector s of m. Now this is a vector. Now I know that we have how many capital M number of messages. So 1, 2, up to, let us say, these are the number of messages, or you can say it's better to write in a different form. Let me write it. Okay, so messages were M1, M2 up to M. Now you know that we have a one-to-one mapping. We have decided that M1 will be represented by S of 1 vector. Okay, this will be represented by S of 2. This will be represented by S of M. So now, because this is now a discrete thing, means M1 was discrete, messages, possible messages were a discrete set, and now this is also a discrete set. Because of one-to-one correspondence, because we have set one-to-one correspondence, now S of k, for k is equal to 1, 2 up to m, are called message points. Okay. Message points / signal points. Now why they are points? Because now they are points in signal space. Okay, because I will say that basically points in signal space. अब आप इस definition को पढ़िए. So the set of signal points / message points corresponding to the set of transmitted signals. So you will know that S1t corresponds to S1. Okay, is called a signal constellation. So this combination or this collection of S1 to Sm will represent a signal constellation. Okay, so ये constellation है. Constellation में you can say that in UPSK how many possible constellation points are there? 4. In DPSK 2. Okay, and in MPSK it will be capital M. Okay, so this is called a single constellation. Now once you try to draw, now what is the meaning of drawing? If I ask you that you draw S1, so S1 एक vector है signal space में, तो इसको draw करने के लिए what you want? You want on the axis you have to draw phi 1t. It means the axis would be of the basis functions. There will be n axis. Okay, so there will be an m dimensional space. So it's an m dimensional space. I can only draw the 3 dimensions here. And let us say there will be some dimension around here, that is some, and this goes on. Let us say this is capital capital NT. Okay, we have assumed that the number of basis functions are capital N. So on this, if I have drawn these as the axis, then I can see what S1 bar means. So let us say some point my S1 bar lies. This is my S1 bar. Okay. This is a vector and this. But this is now called as a constellation diagram. So if we talk of the constellation diagram, this is a constellation diagram. Why? Because we have assumed that we have only 4 possibilities, and I have not yet told you that why only 2 basis functions. We will derive them. That there are only 2 basis functions which are required for the formulation of QPSQ. We will derive it. But anyways, if you right now assume that we have 2 basis functions, then this is the constellation diagram, because on the x-axis it is the first basis function, on the y-axis it is the second basis function. Okay. So with this as a definition of the constellation diagram, okay, let me see. So it's good that we have people attending classes. It at least gives me some audience. Otherwise, I have to record the lecture and nobody would be there. But good, people are attending. So let us come to the concept of signal space diagram or the signal space. Okay. So let us come to this point of signal space diagram. At max we can have drawing of 3 dimensions. Okay. उससे ऊपर हम लोग on paper नहीं draw कर पाएंगे. That I think you may be knowing. So let us first write SIT in a better form. So what is that? If I can apply the formula of cos of A plus B on it, there is a cos of A plus B is cos A cos B minus sin A sin B. Okay. So let us apply that. So let me write cos of A plus B is cos A cos B minus of sin A sin B, the trigonometric equality. If we do that, so SIT comes out to be root of twice of E upon T cos of 2 pi FCT minus root of twice of E upon T sine of twice of I minus 1 pi by 4 sine of 2 pi FCT. Okay, the standard inequality which you use. Now this will give you some sort of a feel of the 2 basis functions. Okay, what would the 2 be? First of all, we have not discussed what. Can you say that this cos of 2 pi FCT and sine of 2 pi FCT are orthogonal? Are they orthogonal? Right now, let us say, may not say that over 0 to capital T, if I talk of orthogonality for the full time, can I say this? So if you have to take the inner product and find out that it should be 0, so suppose I do this. So that should be multiplication. I have to do comma. So this is left as a homework. I think it's a very, very simple exercise. You should do that. So question mark 0. Okay, so this is a homework. So if we choose, let us write this as equation 1. This is suppose 1. Okay. So from 1, we define 2 basis functions. Phi 1 t, which is nothing but root of and phi 2 t sine of 2 pi fc t. Okay, now remember that both of them are defined for x2. Now there are 2 checks. One is that phi 1t and phi 2t are unit energy. So I am doing the check for phi 1t. Phi 2t is quite obvious. What will be the energy? It is 2 upon t integral 0 to capital T cos square 2 pi fct dt. Okay, and this is nothing but 2 upon t 1 plus cos 4 pi fct upon 2. Why? We have used the equality cos 2 theta is nothing but 2 cos square theta minus 1. So if you do that, so this comes up to be 2 upon t into t by 2 plus 2 upon t into sum, you will get sine of theta minus plus I am not putting. Suppose you get 4 pi fct by 4 pi fc, it will be 1 by 2 as well. And if you put 0 to t, then you will find that this sine of 0 is 0 anyways, but sine of 4 pi nc upon t into t. Okay, because this is fc is nothing but nc upon t. So t and t get cancelled. And this, what is this? If nc is an integer, so you know that sine waveform, let us say this is the sine waveform. This starts at 0. Okay, 0, then this pi, then 2 pi. So whether on odd or even, any multiple of pi, the value is 0. Okay, so this is 0. We'll end up with energy as 1. So E of phi to t is a homework. Okay, very simple. Why this is important is this tells us that why this scaling is important. नहीं तो ऐसा लगता है हम लोगों को बड़ा कंफ्यूजिंग लगता है, मतलब जैसे हम लोग इसको स्टडी करते हैं तो हम लोगों को कोई रीजन नहीं मिलता अपराइट कि भाई ये स्केलिंग क्यों कर रहे हैं हम लोग. उसका सिंपल सा एक कारण है, स्केलिंग इज done to ensure that this E of phi1 and E of phi2 are unity. Okay. So another thing to verify is whether they are orthogonal or not. So over this time period you can check. Otherwise, I have given you a standard homework that you check for the complete time period if they are orthogonal or not. But let us say for the time period of our interest, you will check that what is the inner product or by 2t का क्या होगा. सो आप जब करेंगे तो 2 by t 0 to capital T cos of this value into sine of this value dt. So you will check if this is 0. So this is to check. Okay. So this is left as a homework, very simple. I use a trigonometric equality again. This is if you use twice of cos theta sine theta, then you can convert it into some special form and then you can solve it. Quite easy to do that. Now, if that is the definition of now, with the definition of basis functions, message points slash signal points, okay, or the constellation diagram, you can say. Signal points are, so it's the signal constellation. अभी signal constellation आ जाएगा. अब कैसे आएगा? What is SI bar now? This is nothing but root of E cos of twice of I minus 1 pi by 4 and minus of root of E sine of twice of I minus 1 into pi by 4. Okay. This you can directly see from this equation. Anyways, root of 2 by t we have absorbed in this, so only root of E remains. Okay, so this is, let us say, your I is equal to 1, 2, 3 and 4 for the possible values of I. So this is the way we generally define the constellation or generally study, you can say, modulation schemes, because this puts up a nice structure on them, and their study now can be done in the Euclidean space. And you know that whatever transmitter or receiver we were using, means typically we would say we will first multiply the transmitted information with the cosine waveform, and at the receiver, as you know in the case of analog modulation, that you multiply it with the same carrier to recover the information. So this operation can now have a corresponding analog with the correlation operation in the Euclidean space or in the vector space. So वो उसी तरीके से हम लोगों ने we have studied all of them. Okay, आप इसको analog communication से you can draw some parallel. Okay, yes. Let us just write S of I1. Let us make this table. This will clarify a lot of things. So what is S of I1 and S of I2? So it will be root of E by 2. This is minus root of E by 2. Then minus root of E by 2. This is E by 2. Minus. This is minus root of E by 2. And then this is root of E by 2. And this is root of E by 2. And this is root of. How do you do that? Just simply put the values of I in it. So once is cos of pi by 4, then it is cos of 3 pi by 4, then it is cos of 5 pi by 4, and this is cos of 7 pi by 4. So you will find that it has only two possible values. So let me write. So cos of 2i minus 1 pi by 4 for I is equal to 1, 2, 3 and 4. 1, 2, 3 and 4 has only two possible values. Or let me write in a well-defined way that it takes values among the two possible values. That would be a better English to write it. Takes values from the two possible values. Root of 1 by 2 and minus root of. Okay, I think if you remember what is one's one, it means I think you can relate it from class 12 that we used to write the cosine and sine table. So we used to mug it up. So you can check what is cos of pi by 4. I think the way to write it was, if I relate it to our 11th or 12th class, then this is not the way we used to write. We used to say 1 upon root 2 and minus 1. So I am writing in that manner so that it's easy to relate. Otherwise, that will lead to the same result, 1 by root 2 and minus 1 by. So आप check कर सकते हैं. And the same applies for. And the same applies for sine of twice of I minus 1. इसमें भी दो ही possible values आएंगी. That is 1 upon root 2 or minus 1 upon root 2. Now, one important observation about this set is, one important observation which we can make from this set is, one important observation from this set is, it is something like this. It means basically the two values are 1 and minus 1 only, and this is like a constant. Okay, it means it doesn't change the polarity. So if I just take this root 2 inside it, so this has only two, plus 1 minus 1. This is plus 1 minus 1. Why I am doing this is, I am observing that this is what is happening. Now this says that this is nothing but two BPSK systems. We will see it later. Okay, I have just written it for the purpose of referring it later. Okay. So now I can give them a name. Now I can properly draw these points. Let us say this is my root of e by 2. This is my root minus root of e by 2. This is my plus root of e by 2. And this is my minus root of e by 2. Okay? So now this is my one point. Then this is my second point. Let us say this is my third point and this is my fourth point. Okay? So let us give them some name. P1, P2. So I am giving them like this. This is P1. This is P2. This is P3. And this is P4. So on this diagram, this is P1. This is P2. This is P3. And this is P4. Now this is the constellation diagram. Okay. So this is constellation diagram. For QPSK with this as the choice of the phase angles. Okay, मतलब जो हमने choice ली है वो ये वाली ली है, pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. We have not yet taken this as a choice. Okay. उसको choice लेंगे तो वो बदल जाएगा थोड़ा सा इसका जो expression है. Now it will have, मतलब you have points here on the axis. The points will lie, and the other coordinate will be 0. So this will be root of e by 2 0. Then this is minus root of e by 2 0, then it will be 0 root of e by 2 and 0 minus root of e by 2. Okay, so we will have that way the constellation can be written. Okay. Yes, so let us now discuss the error probability. Okay, अब हम लोगों का constellation diagram we have just drawn. I think whatever base was required we have built. Or what we can do is we can just refer to the textbook and see one of the figures of how this feels. Let us do that. Let us see that. This is given the figure 6.7. Yes. So let us say what do we do is that this is the bit sequence which is coming. If that is the bit sequence which is coming with us, so what do we do is we take 0, 1, 1 and 0. That is every alternate bit, or you can take every odd numbered bit. We say that this is one of the possible waveforms, and then the second is every even numbered bit you take. Okay, so 1, then 0, then 0 and then 0. So you create two possible waveforms and you add both of them to generate your ST transmitted waveform. You can just take a look for some time, maybe for 1 or 2 minutes, then we will start. Now you can say that this from this to this is a symbol time. From this to this is a symbol time. So you will see that at the symbol time, there is an abrupt transition. Okay, it means another cycle starts, but it starts from a different point. Okay, so this is the way the waveforms are really. This you can see in oscilloscope as well. And once you add both of them, you will get the net S of t. So you will see that these are the transitions which are happening. Okay. So let us go back and first of all let us discuss the error probability of QPSK. Now this would be interesting to study because we did all of our ML and map decoder. Now let us see how it applies to this constellation scheme. So let us say what do we receive? X of t is nothing but SIT plus W of t. Okay, and we are obviously interested in an interval of 0 to capital T where I is equal to 1, 2, 3, 4. Okay, this odd and even number I will just basically elaborate on it either today or maybe in the next recorded lecture. So I am not right now going into that why did we do an odd numbered scheme, then even numbered scheme, and then generated the waveform. I will elaborate on it, but first of all, let us do the error probability. This is more important, okay, right now. So what is x1? You do the correlation of xt with one of the basis function. So you will land up with, so I am not solving it, or okay, let me write it. So this is root of e cos of twice of I minus 1 pi 4 plus w1. Why? Because the component of x of t or the component of SIT along phi 1t is this. This you can see from this. Okay, this is the component of SIT along phi 1t. Now, if I check for over I is equal to 1, 2, 3, 4, I know that this has only two possible values, that is plus 1 by root 2 or minus 1 by root 2. So I can write that x1 is nothing but plus minus root of e by 2 plus w1, because it has only four possible values. It has only, or it takes values from, okay. Now let us find x2. x2 is what? It is, again, you will just find the corner, you will project it along the second basis function. This you will land up with minus of root of e sine of plus w2. Okay, and now there is one thing, this is minus plus root of e by 2 plus w2. Now this minus, see, this is plus minus and this is minus plus. Okay, now this represents that, first of all, if I am considering the value, then it is plus I will consider first, and then minus, and here it is this just simply is to take this minus into account. Okay, if I assume that cos and sine, if suppose this is the set, then I will say that this value will belong from minus 1 by root 2. We'll just put in some hierarchy over it. Okay, if 1 by root 2 है minus 1 by root 2 है, ये minus 1 by root 2 से मतलब minus 1 by root 2 or 1 by root 2 value लेता है. Just to highlight this, we have just put a minus plus here. This doesn't change much of the things. Okay, it means it's plus minus, then it is plus plus minus plus minus minus. Okay, that is the way you can see this. This will basically give us this diagram. It is plus minus, then minus minus, minus plus, plus plus. Okay, or if you say that this would be plus minus, then this minus will change the polarity. Okay, so in order to incorporate this minus, we have done this. Okay, now if that are the two components, that is, we have received now x bar. So x bar is nothing but it is plus minus root of e by 2 plus w1, and this is minus plus root of e by 2 w2. Now you will apply the, if you choose ML as the decoding or detection criteria, as the decoding or detection scheme, then find norm of x bar with all the possible points p of I. Okay, I is equal to 1, 2, 3, 4, and choose that I which leads to मिनिमम दिस, वो आप आई चूज करें जो कि सबसे नजदीक, मतलब जैसे आपने देखा x कहाँ लाई कर रहा है, यहाँ पे ये ऑब्टेन किया आपने वेक्टर, एंड आफ्टर ऑब्टेनिंग दिस वेक्टर जस्ट फाइंड इट्स डिस्टेंस फ्रॉम ऑल द पॉइंट्स, जिसका सबसे कम डिस्टेंस आए वो आपने चूज किया, दैट इज व्हाट योर एमएल क्राइटेरिया सेज। नाउ बेस्ड ऑन दिस can we find / draw the decision regions ZIs? मीन्स अगर हम ये बताना चाहें, जैसे पूरा स्पेस हमारे सामने है 5 1 5 2 2 डायमेंशनल स्पेस, वी कैन ड्रॉ, वी कैन विजुअलाइज, सो कैन वी ड्रॉ बाउंड्रीज? इट मीन्स हम ये बना दें कि अगर हमारा x इस रीजन के अंदर है तो P1 सिंपल, तो कुछ नहीं देखना है, फिर हमें बस ये चेक करना है कि ZX जो है कहाँ लाई करना है, किस रीजन में, तो हमें मिनिमम डिस्टेंस इस तरीके से निकालना नहीं पड़ेगा। इसका मतलब ये कि हमें पूरा ये i = 1 to 4 का कैलकुलेशन रन नहीं करना पड़ेगा। व्हाट वी कैन डू सिंपली चेक इज कि x कौन से रीजन में। So based on this minimum distance criteria, what I can say is that for this point constellation, if this is the point, this is the point, this is the point, and this is the point, intuitively I will say, if at all, I will say for any point here, the distance of this point from this will be minimum as compared to its distance from this, this, and this. And this happens for all the points who are in this quadrant. Okay, so this is your decision region 1, or you can say Z1. So if this comes from the minimum distance theory, so this is your Z1, then this is your Z2, and this is your Z3, and this is your Z4. The same applies for P3. मीन्स जो ये रीजन है, इस रीजन में अगर आपका x लाई करता है, तो आप सिंपली आप कह सकते हैं कि P1 ट्रांसमिट हुआ होगा। अगर आपका x इस रीजन में लाई करता है, इस क्वाड्रेंट में लाई करता है, सो द 4 quadrants are the decision regions for the points P1, P2, P3 and P4. Why? The question is why. So why? Because if at all we have made the minimum distance as the criteria for selection, so we have to prove that, let us say example लेते हैं, for example consider x bar lying in Z1. Okay, now assume that x bar lies in Z1. So we have this is your point P1, and suppose this is your Z, x bar. Okay. So we have not yet proved this. Basically इसका एक proof है proper. This proof we generally do in postgraduate course on digital communication. So I am going to be doing it right now. Basically I have done it in the MTech course as well, but that is somewhat involved, and I don't think that is required here. You can just feel basically an intuition also. Okay, so this, let us say this is point P2, this is P. So you can say that if I choose distance as the criteria, P3, and this is, suppose this is P3 and this is P4, then the decision boundaries are given by the perpendicular bisectors of the line connecting the 2 points. So suppose this is what is, but draw the perpendicular bisector, and this is, draw the perpendicular bisector, and this is, then draw the perpendicular bisector. So they meet at this point. Okay, now they have implicitly created the decision regions. This says that अगर point यहाँ lie करता है, तो उसका जो distance होगा P2 के साथ वो सबसे कम होगा as compared to its distance from other points. points. Okay. So decision boundaries are given by the perpendicular bisectors of the line connecting constellation points. Okay. So I am not giving the proof not required, but interested reader can see Proc's 5th edition, not the edition we are following. We are following 4th edition. We are following basically, I can write it down. This is digital communication. See? Digital communication by Prof. Okay, you can see that textbook, 5th edition, the proof you can find there. So these are the decision regions. Now, अब error probability निकालनी है. So average probability of error. I think we discussed this. You can refer to lectures held before or conducted before. I should have lecture notes. Okay. You can refer to lecture notes. So the past lectures. Why? Because we covered that. अगर आपने डिसीजन रीजन्स बना लिए हैं तो डिसीजन रीजन्स के बाद आप प्रोबेबिलिटी ऑफ एरर कैसे निकाल सकते हैं उसका हमने स्ट्रेट फॉरवर्ड फार्मूला दिया था दैट यू इंटीग्रेट द कंडीशनल प्रोबेबिलिटी ओवर द डिसीजन रीजन्स. ओके, दिस कैन बी डन. ओके, दिस मींस इट कैन बी इजीली डन. बट QPSK में एक फायदा है. QPSK द वर्क रिड्यूसेस अ लॉट. व्हाई? लेट अस फाइंड एन इक्विवेलेंस. ओके, this can be done. Evaluate कर सकते हैं. डिसीजन रीजन्स की थ्योरी हमें समझ में आ गई, हमने बना ली है तो निकालना आसान है. बट कैन वी मेक आवर वर्क इजियर? यस. सो वी विल सी दिस दैट कोहेरेंट QPSK is equivalent to, so this is equivalent to coherent BPSK systems working in parallel and using two carriers that are in phase quadrature. Okay. Now, this is also called as, let me write it down. I think I want to turn. Quadrature carrier multiplexing. Now ये जो टर्म्स आई हैं इनका मीनिंग क्या है? फर्स्ट ऑफ ऑल हमने अभी तक QPSK को डिफाइन नहीं किया था. QPSK is nothing but quadrature phase shift keying. Okay. Now there is one thing. If I consider the variation of theta from theta varies from 0 to 2 pi. So what is pi by 4? So what is pi by 4? It is 1 by 4 times 2 pi. Okay, or it is 1/4 of 2 pi. And what is quadrature? Quadrature is the same thing, 1/4 of 2 pi. So this quadrature says that there will be something which is, sorry, it is pi by 2, not pi by 4. So if I draw it pi by 2 here, this is pi by 2. So this angle pi by 2 is 1/4 of 2 pi. मतलब एक complete cycle का 1/4 है. So quadrature means चौथा हिस्सा. Okay. So चौथा हिस्सा कैसे बोलेंगे? आप देखिए, अगर आप cos और sin को देखें, what is cos and sin? Plus minus pi by 2, whatever. It gives you sin theta. I am not writing the sign, I am just missing it. Okay. So cos and sin are at phase quadrature, means 1/4 of 2 pi से differ करते हैं. So जहां पे भी ये quadrature वर्ड आता है, इसका मीनिंग ये है कि cosine and sin are involved, or there is something which deals with pi by 2. So this quadrature here is nothing but which deals with pi by 2. Now what is the meaning of quadrature? Carrier. It means the carrier way. We can use two carrier waveforms, or we will be using with two carrier waveforms which differ in pi by 2. So कौन सी दो waveforms use करी हमने? यहाँ पे आप देख सकते हैं. One is sine and one is cosine. This is cosine and this is sine, and they differ with each other with pi by 2. That is quadrature of 2 pi. So this is quadrature. So quadrature comes from this pi by 2. Then this carrier is, we are using two carriers which are at quadrature, and multiplexing now means that we will be multiplexing our input bit streams into the two bit streams with each modulating one of the carrier. Okay, so that is the meaning of quadrature carrier multiplexing. Now why quadrature phase shift keying? Okay, अब आप इसमें क्या कर रहे हैं कि आपके पास you are having two carriers, and of the two carriers you are changing the phase, and these two carriers are at quadrature of each other. Or let us see this. Let us see this expression. Yeah, this expression you can see. So we have two carriers, one is cosine, one is sine. This is the standard QPSK system, okay? And you obtain it by changing the phase, okay? So this is what the way to obtain it is this. You are taking a waveform and you are just changing its phase. So it's, and that too in a discrete sense. We have only 4 possibilities. So this leads to two carriers at quadrature, which is cosine and sine, and their phases change, because आप इसको यहाँ पे प्लस और माइनस ही आएगा, +1 -1 will come. You have seen that it takes only two possible values. I have just written it here for you, these two possible values. It means जो दो क्वाड्रेचर पे कैरियर्स हैं, कायदे से उनका बस फेज बदल रहा है आपस में. क्वाड्रेचर पे तो है, बट एक दूसरे का कोसाइन का भी फेज बदल रहा है, साइन का भी फेज बदल रहा है, और वो कीइंग के मैनर में बदल रहा है. So that is why this is called as quadrature phase shift keying. So now we have defined. So each of the word has a meaning. Now if you go back and read it, I will say that you will definitely understand it. Okay. Or if at all there is any doubt, definitely we can discuss. Okay. So let us see. So if this is the case, then x1 is the output of first coherent BPSK system, and x2 is output of second अगर ऐसा होगा, मतलब मान लीजिए कि ये कैसे, अब इसको एब्जॉर्ब करने के लिए एक चीज देखते हैं हम लोग. मैंने यहाँ पे पहले ही लिखा था कि अगर आप 1/√2 को बाहर लिख लें तो ये +1 और -1 है. अब इफ यू गो बैक एंड रीड द PPSK system which we discussed, so what was happening in that system? So you have two possible waveforms. One is S1T, which is +1 times this, and S2T which is -1 times this. Okay, so +1 -1 +1 -1, there are two possible choices. Now if we try to draw an analog here, then if I absorb 1/√2, so there are only two possibilities. Let us say अगर मैं आपको यहाँ पे कहूँ कि आप इस पूरे P1 P2 को क्या आप ऐसे लिख सकते हैं? Yes, you can definitely write. So 1 by, what you can say, root of E by 2 times. So that is your set now. P1, P2, P3, P4. Okay, that is 1 and 1, then -1 and 1. Okay, then it is -1 and -1, and then it is 1 and -1. So ये क्या है? ये एक BPS के सिस्टम है पूरा, क्यों? क्योंकि +1 -1 there are two choices. This is also a BPS का सिस्टम. Okay, why? Because only +1 -1 +1 -1 are the two changes which are happening. So और ये किस पे हो रहे हैं? कैरियर्स पे. अगर मैं कोसाइन को सेपरेट कैरियर ले लूं, अगर आप इसको देखिए, ये जो चेंज हो रहा है ये कोसाइन पे हो रहा है. यहाँ पे इसमें क्या पॉसिबिलिटीज आ रही हैं? सिर्फ +1 -1 +1 -1 कोसाइन के साथ, और मैंने रिसीवर पे कोसाइन के साथ मल्टीप्लाई करके इसे सेपरेट कंपोनेंट के रूप में आई ऑलरेडी एक्सट्रैक्टेड दिस आउट, बिकॉज दिस एंड दिस आर ऑर्थोगोनल टू ईच अदर. And this I have separately extracted it out through x2. Okay, and this has only two possible choices: +1 -1 +1 -1. Okay, and this is your sinusoidal waveform. और इसका जो ये वाला कोफिशिएंट है, ये सेपरेटली हम एक्सट्रैक्ट कर पाए हैं थ्रू अवर कोरिलेशन. ये आपने यहाँ देखा, हमने x2 को अलग से निकाल लिया है विदाउट एनी इंटरफियरेंस फ्रॉम द कंपोनेंट ऑफ x1. सो इसका कोई इंटरफियरेंस नहीं, तो ये दो इंडिपेंडेंट आपके पास वैल्यूज आई हैं, x1 and x2. So that is what is the analog is. It means it is equivalent to two coherent PPSK systems working in parallel. Okay. So with this as the case, we can. Why did we do that? Because अब आप आसानी से error probability define कर सकते हैं. But there is a change, because this is having an energy of E/2 now. हमने जो पढ़ा था BPSK, उसके अंदर जो energy थी, that was that was EB. I think I must have, yeah, this was the bit energy EB, but now the energy would be E/2. Okay, so we will be closing this class. Just I think after writing 3-4 lines, we are done with QPSK mostly. All the remaining things we will get in the recorded lecture. For each BPSK system, energy per bit is equal to E/2. It should be, because हमने सिंबल एनर्जी बोली है E, और ये अब हम एक कंपोनेंट की बात कर रहे हैं, तो दोनों कंपोनेंट की एनर्जी मिलके कैपिटल E होनी चाहिए, तो इसलिए एक एक कंपोनेंट की E/2 होगी. और नॉइज का जो PST वो तो N0/2 ही रहेगा. N0 PST is N0/2, because we have seen that if you project white Gaussian noise on any of the, you can say, basis functions, you will land up with a random variable that has a mean of 0. If at all your WT is of 0 mean and PST is N0/2, so the variance would be N0/2. This I have proved. So if you, at all you are following the lectures, you are reading them, or you are going through the textbook, you can appreciate it. Okay. And one point is this. Second point is, for each system, average, this we derived in the last lecture, average probability of error is equal to 1/2 ERFC root of E/2 N0. Why? Because E/N0 थी error, but अब E/2 अगर आप लेके चल रहे हैं एनर्जी को, तो E/2 N0 would be the answer. Okay, so this is P of E for each of the system. So now bit errors in the in phase then quadrature channels of the coherent QPSK system. Why coherent? Because we are using the carrier waveforms at the receiver to decode it. Because हमने x1 x2 obtain किया, ये माना है कि आपके पास phi1 phi2 का exact value available है, are statistically independent. Now why? So there is another why which pops up. Independent. Okay. Why? Because x1 x2 are projections of the waveform along two orthogonal directions. मतलब जो x1 आया है आपका, let me just go back to this. Yeah, this is x1. So you have projected x of t onto phi 1t. So जो component है x का वो along phi 1, जो ये आपने x1 obtain किया. ऐसे x2 जो है वो component है along phi 2. So phi 1 phi 2 तो दोनों orthogonal है. तो अब आप x1 का कोई भी decision लेते हैं x1 के basis पे, that won't be impacting your decision once if you take it on the basis of x2. So they will be statistically independent. Okay. So I am intuitively saying this, although you can definitely prove it. Okay. कोई इसमें हम लोगों ने काफी इसमें analysis किया है, आप आसानी से इसको prove कर सकते हैं. So in phase, so when we just take the in phase component, so in phase decides on one of the bits, okay, and quadrature phase decides on the other bit. So what is the probability of correct decision in QPSK? It is nothing but there is no or correct decision in channel, in phase channel into correct decision in out phase channel. Probability of correct in phase into probability of correct quadrature phase. Okay. This we know is nothing but 1 minus PE into 1 minus PE. What is PE? PE you can obtain from here, because each of them is a BPSK system. And this is peak and this is average probability. Note that average means over the all possible constellation points. Okay, so this is nothing but 1 minus PE whole square. Now average probability of error QPSK is nothing but 1 minus P of average probability of correct decision in QPSK. This is nothing but 1 minus P is whole square. Okay, so this is nothing but 1 minus ER 1 by 2 ER FC okay. So this is your easy way to obtain the error probability of a QPSK system. We have just drawn an analog between QPSK and BPSK systems. Although you can land up to the same answer if you derive in this way. It means आप decision regions के ऊपर भी इसको derive कर सकते हैं. Okay. So I think we are done with the QPSK. But there are two important things which are remaining. One is a power spectra of each of BPSK and QPSK. And I got to know from section B that some part of information theory would also be covered. Anyways, whatever is remaining, maybe a few parts, I will cover in the recorded lectures, which I plan to upload by the middle of next week. Then you can go through them. I think it would be at max 3 lectures, if it required. Otherwise, it can be done in 2 lectures as well. So I will look into it. So I think we are done with the course now. So I would wish you all the best. Okay. So
what will be the syllabus for the exam and the exam pattern?